Hello, everyone. So today let us continue our discussion on the oxyacids of nitrogen. And let us go to the next prominent oxyacid of nitrogen, and that is nitric acid, which has a molecular formula of HNO3. This is the basic molecular formula. So we will start with drawing of the structure by using VSEPR theory. So for VSEPR theory, first thing that we do is count the number of valence electron, and we counted it, and we found it to be 24 valence electrons present. Okay. Now the next step is to find out a basic skeleton with the central atom. So we know least electronegative, apart from hydrogen, is nitrogen. So nitrogen would be our central atom, and therefore we draw the nitrogen atom at the center, and then we draw the other 3 oxygen atom around it, and then we have the one of the hydrogen, only one hydrogen is present, and that we attach to oxygen because it being a acid. Okay, so this would be the basic structure, and then what we do is we will join each atom via a single bond. So there are total number of 4 single bonds, so that means 4 bond pairs, so we have to account for 8 electrons. So we subtract from the number of valence electron 8 electron, and we found it to be 16. Next step is arranging these 16 electrons as pairs of electron on the other atom. So we start with oxygen atom. So I arranged these 16 electrons as pairs around the oxygen atom, and I almost completed the number of 16 electrons. Thereafter, now we look for whether every element in this particular structure is having an octet or not. So when I check it, I found that nitrogen is not having the octet when I drew the structure in this particular format. So what I did, one of the lone pair I transferred as a bond pair, and I got a double bond here, and then every atom now is having an octet of electron around it. Now I calculated the formal charge. Nitrogen has a formal charge of +1. This oxygen has a formal charge of -1. The rest of the oxygen atom is having a formal charge of 0. Overall, this particular nitric acid from this Lewis structure is electrically neutral, as it is to be. Now, once we got there, next thing we have to do from this Lewis structure is now to find out the shape of the molecule. So when we look at the central atom, we find that it is attached to 3 bond pairs. Okay, so 3 bond pair means the shape according to VSEPR is trigonal planar, and that is why I drew in this structure in a trigonal fashion. So nitric acid, the shape is trigonal planar. So VSEPR theory pretty well account for the trigonal shape of the nitric acid. Coming to the various resonance structure that you can draw, this is pretty familiar to you. So 3 different resonance structures we can draw, and then this would be the hybrid structure of the nitric acid that can be drawn. As you can see from these, all these 3 structures, that all these 3 structures is electrically neutral because we have one positive and one negative charge, so both of them are electrically neutral. And here also there are 2 positive charge and 2 negative charge, so therefore this structure is also electrically neutral. However, this structure contributes less to the resonance because of the too much charge being generated on this structure. So ultimately, the double bond is kind of delocalized over all these particular bonds that are attached to the central nitrogen atom. So this clearly indicates the structure and the resonance of the nitric acid. Now coming to how to solve it using VBT, we find that if we have to solve it using VBT, we have to first consider the central atom. And when we consider the central atom, we have to first find out the ground state electronic configuration. So that is what I have written down here. So we see I have written down the electronic configuration as 2s2, 2p3. Similarly, The other atom is oxygen, so it has a ground state electronic configuration of 2s2, 2p4. Perfectly fine with these structure. Now, next step that we have to do is find out how many bonds that this is attached to. So if we look into very carefully, we find that it is bonded to via to 3 oxygen atom via looks like it is via 3 sigma bonds is what is formed. So if 3 sigma bonds is formed, we require three unpaired electrons. So if we have to include 3 unpaired electrons, the hybridization should become sp3, which is not the case. We know that from VSEPR theory, the shape is trigonal planar. So obviously the hybridization should turn out to be sp2. So that means one of the sigma bond is not actually a sigma bond, but a different kind of bond. So that means we have to now take into account only 2 sigma bonds. So if we take into account 2 sigma bond, we have sp2 hybridization happening, and we have this particular way in which we write the electronic configuration. Now, when we form the nitric acid, it is important to see what is happening, like what is the nature of the bond to all these 3 oxygen atoms, which will help us to understand in detail what is the nature of the bond. So when we talk about the 2 unpaired electron, it is definitely involved in some kind of sigma bond. So obviously, like in the nitrous acid, we have 2 sigma bonds. These would be the 2 sigma bonds to the oxygen. So that I have drawn these electrons are the green electrons are the electrons from the oxygen, and they form the necessary sigma bonds. So let's look into this, this oxygen with a red star, this oxygen with a green star. So when we look at first the red star oxygen, we find that that is attached, that will show a hybridization because it is attached to nitrogen by a 1 sigma bond. So we need to include only 1 unpaired electron. So the hybridization would be sp2. So that is what I have drawn here, sp2 hybridization. And then what happens, you will have this electron coming from the nitrogen and pairing up. So this oxygen will have form a 1 sigma bond to the nitrogen atom, and then it has an unhybridized p orbital. Similarly, on nitrogen we have an unhybridized p orbital, and they can form the p pi pi overlap to form the corresponding double bond with the red oxygen. Okay, now let us look at the green oxygen. So green oxygen is pretty simple because it is forming 2 sigma bonds, one with hydrogen and one with nitrogen. If we want to include 2 unpaired electrons, the hybridization should be, we should choose as sp3. So when we choose sp3 hybridization, this is the hybridized state. So the 2 electrons are one pairing up with the nitrogen and one pairing up with the hydrogen. So we have a perfect bonding accounted for the red oxygen as well as the green oxygen. Let us look at the black oxygen. Okay, this one will give us an indication about what is the nature of bond that is formed in here. So if we look carefully, we find that the lone pair that is on the nitrogen here is actually kind of coordinating with the forming a coordinate bond with the oxygen. So when it is kind of coordinated with oxygen, these 2 electrons that are present, which are unpaired, become paired, and then one vacant orbital is generated here, which is then occupied by the lone pair that is donated by the nitrogen. So basically, if you exactly want to say this particular bond is not a sigma bond, but rather it is a coordinate bond where the lone pair that is present on nitrogen is kind of donated into the vacant orbital on the oxygen atom. So this particular bond is not a sigma bond, but rather a coordinate bond. So this gives us a pretty much idea about the nature of the bonds that are formed. We have a 2 sigma bonds and 1 pi bond and 1 coordinate bond that is formed in the nitric acid. So that is what VSEPR can give us a basic idea about the structure, but VBT is the one that will give us an indication about the type of bond that is formed and nature of bond that is formed. That is what is important to understand. And when we go from BBT to molecular orbital theory, it becomes more clearer, like how the orbitals are actually interacting. But BBT gives a very close indication to molecular orbital theory. Now, coming to the acid strength of these oxyacids of nitrogen, we find that we can define the acid strength on two things. One is the basis on the basis of stability of the conjugate base. So if your conjugate base is stable, then that means they are more acidic. So here we have to compare nitrous acid and nitric acid. So we when nitrous acid undergo deprotonation, it forms the nitrous ion, and this nitrous ion has these two resonance structures, and this is the hybrid resonance structure. Now coming to the nitric acid, when it deprotonates, it forms nitrate ion, and these are the three resonance structure that you can draw for the nitrate ion, and this is the hybrid structure. So if we compare these two, if we compare the stability of these two conjugate bases, obviously nitrate is more stable, involves three resonance structures. Apart from that, this structure is more symmetrical and more delocalized in comparison to this particular hybrid structure for the nitrous ion. And therefore we have nitric acid being more stronger acid than the nitrous acid. Second basis on which we can find out whether they are more acidic is on the basis of ionizability of this OH bond. This depends upon how much electronegative this oxygen atom is. More electronegative this oxygen atom, this would be more prone to ionization and therefore act as a stronger acid. So if you compare the oxidation state of these two nitrogen atoms, what we find is if we write down the oxidation state of this particular nitrogen atom, it should be 1, 2, 3, P2s are 6, -1. So this would be +5 oxidation state in case of nitrogen. And if we compare nitrous acid, 2, 2s are 4, so it would be +3 oxidation state. Okay, so more electronegative nitrogen is the one with a higher oxidation state. This electronegative oxygen would be more prone to more electronegative on account of the higher oxidation state of this particular nitrogen atom, and therefore this OH bond is more ionizable because this nitrogen is more has a more higher oxidation state, so that makes this oxygen more electronegative, and therefore this hydrogen more ionizable, and therefore we get the fact that nitric acid is more acidic than the nitrous acid. Now coming to so these are the two bases in which you can tell about the acid strength of any particular acid, on the basis of the conjugate base or on the basis of ionizability of the OH bond. Then there are two less prominent acids. One is the hyponitrous acid, which has a general formula of H2, molecular formula of H2N2O2. Similarly, there is nitrooxalic acid, which is H4N2O4. So this structure I have drawn for the hyponitrous acid very simply using BSEPR theory. First, I calculated the valence electrons. I found out to be 24. I arranged these atoms in the best possible way, keeping the nitrogens to the central atom. We know that it is a dibasic acid, so only possible way we can draw it as a dibasic acid is in this format. Next, after putting 1, 2, 3, 4, 5 bond pairs means 10 electrons, so that after subtracting them, we are remaining with 14 electrons. I arrange them around the oxygen and then around the nitrogen, and I found that this particular nitrogen atom is not having octets, so I transfer this electron, so we got this particular structure. Now if we calculate the formal charge, every atom is having a formal charge of 0, so that means this is a very correct Lewis structure that we have drawn in here. So this is a very less stable acid. It just decomposes very quickly. to corresponding nitrogen and water. Similarly, this is another acid, it is nitrooxalic acid. Now I would like you to do, using BSCPR theory, try to find out the structure of H4N2 O4. Okay, so that's all about the oxyacids of nitrogen. I hope this thing is pretty clear to every one of you. You can do for any oxyacid. Now, in the coming lectures, we are going to concentrate on oxyacids of phosphorus, and there you would understand that it is very easy to find out the structure of the compound, and you don't have to every time remember all these things. If you understand VBT, if you understand BCPR, it is very easy for you to easily predict the structure of any given molecule. Okay, so let us, I hope that this particular session has helped you to understand broadly how to draw a Lewis structure, how to make the VBT, use of VSAPR and VBT to find out the structure of the molecule. So this is what you have to keep in mind. These things you should never forget. All throughout your chemistry career, you're going to need to use them in various places. Okay, so I hope this lecture has given you a good indication of that. So till then, have a nice day. We'll meet in the next video. Thank you very much.